Welcome to Senior High School Math Series. Let us have Ellipse Part 1 with center at the origin. Under Pre-Calculus Quarter 1 Week 3, based on Curriculum Implementation and Learning Management Matrix for K-12's most essential learning competencies. Here are our learning competencies. Define an ellipse and determine the standard form of equation of an ellipse. Before we continue, let us ponder on this. Whoso loveth instruction loveth knowledge, but he that hateth reproof is brutish. From Proverbs chapter 12 verse 1 of the King James Bible. Let us have a recall. During the presentation on the derivation of the equation of the ellipse, if you haven't seen it, the link is on the description of this video. We derived the equation of the ellipse based on its definition. We set a string fastened on two fixed points on the plane called foci. With the string taut, a point P on the same plane moves, and the curved trace was an ellipse. We set the distance between the two fixed points as equal to 2c, and accordingly, the coordinates of the foci f prime is negative c0 and f z0. Hence, the distance between the origin or the center of the ellipse and the foci is c units. Now consider the point P at the point x0. You will notice that there is an overlap of the string from point P to point F. And since we set the sum of the distances PF prime plus PF is equal to 2a, then the distance between the origin and the point x0 is equal to a units. Now let point P be on the point 0y. Since PF prime plus PF is equal to 2a, then at this position of point P, PF is equal to a unit. Also, the distance between the origin and F or F prime is c units. Hence, A is greater than C. The distance from the origin to the point 0y completes a right triangle. Remember, in the derivation of the equation of the ellipse, we set another variable as B. Now, the relationship between A, B, and C is therefore given by the Pythagorean theorem. Hence, b squared is equal to a squared minus c squared. Now let us have the definition of an ellipse. An ellipse is the set of all points P in a plane such that the sum of the distances of P from two fixed points of the plane is a constant. Let us go back to the equation of the ellipse. When the line containing the foci is the x-axis, and since the origin is midway the foci, the center of the ellipse is at the origin. The equation is x squared over a squared plus y squared over b squared equals 1. When the foci is contained by the y-axis, the equation is x squared over b squared plus y squared over a squared equals 1. Let us have the properties of the ellipse. of the equation x squared over a squared plus y squared over b squared equals 1, where a is the distance from the origin to the point x0 of the ellipse, and b is the distance from the origin to the point 0y of the ellipse. Observe that the graph of the ellipse is symmetric with respect to both coordinate axes, such that when y is equal to 0, x is equal to positive negative a. So we have the vertices at a0 and negative a, 0. Also, when x is equal to 0, y is equal to positive negative b. Hence, we have the co-vertices at points 0b and 0, negative b. The ellipse cuts the x-axis at its vertices b a0 and b prime negative a0. The distance between the vertices is the major axis of the ellipse. Hence, the major axis is of length 2a. Also, the ellipse cuts the y-axis at its co-vertices b prime 0 negative b and b 0 b. The distance between the co-vertices is what we call the minor axis of the ellipse. Hence, the length of the minor axis is equal to 2b. The foci of the ellipse are at the points f prime negative c0 and f c0. The intersection of the axis is the center of the ellipse, this time at point 0, 0. The chords of the ellipse passing through the foci and perpendicular to the major axis is what we call the latus rectum. The ends of the latus rectum may be obtained by substituting x equals c to the equation x squared over a squared plus y squared over b squared equals 1, and using the relation c squared is equal to a squared minus b squared. Hence, the ends of the latus rectum are at the points negative c, b squared over a, negative c, negative b squared over a, and c, b squared over a, and c, negative b squared over a. The length of the latus rectum may be obtained from the coordinates of its endpoints. Hence, the length of latus rectum is equal to 2b squared over a. This time, let us have the properties of the ellipse of the equation x squared over b squared plus y squared over a squared equals 1. This time, a is the distance between the origin and the point 0y of the ellipse, and b is the distance between the origin and the point x0 of the ellipse. The graph of the ellipse is symmetric with respect to both coordinate axes, such that when x is equal to 0, y is equal to positive negative a. Hence, the vertices of the ellipse are at 0a and 0 negative a. When y is equal to 0, x is equal to positive negative b. So the co-vertices of the ellipse are at b0 and negative b0. The ellipse cuts the y-axis at its vertices v prime 0 negative a and v 0a. The distance between the vertices is the major axis, hence the length of the major axis v prime is equal to 2a. Also, the ellipse cuts the x-axis at its co-vertices b prime, negative b0, and b0. The distance between the co-vertices is the minor axis, hence the minor axis is of length 2b. The foci are at 0, negative z, and 0, c. The intersection of the axis is the center at 0, 0. The chords perpendicular to the major axis and passing through the foci is what we call the latus rectum, and the coordinates of the ends of the latus rectum may be obtained by substituting y is equal to c in the equation x squared over b squared plus y squared over a squared equals 1, and also using the relation c squared is equal to a squared minus b squared. Hence, the ends of latus rectum are at negative b squared over a, c, negative b squared over a, negative c, and b squared over a, c, b squared over a, negative c. The length of the latus rectum may be obtained from the coordinates of its endpoints. Hence, the length of the latus rectum is 2b squared over a. Let us have an example. Find the equation of an ellipse with foci at 0, positive, negative 4, and a vertex at 0, 6. We have our given information. F prime at 0, negative 4, F at 0, 4. Also, we are given a vertex at 0, 6. Since the foci lies on the y-axis, the major axis of the ellipse is along the y-axis. Hence, we have the standard form of the equation as x squared over b squared plus y squared over a squared equals 1. And since the center is midway between the foci, we have c is equal to 4. And the vertex is at 0, 6. Then we have a is equal to 6. To find the equation, we now only need the value for b, and using the relation b squared is equal to a squared minus c squared, substituting the values, we have b squared is equal to 6 squared minus 4 squared. So we have b squared is equal to 36 minus 16. 36 minus 16 is 20. Getting the square root of both sides, b is equal to positive negative 2 square root of 5. Hence, we have the equation as x squared over b squared, that is equal to 20, plus y squared, a squared is equal to 36, equals 1. Example number 2. Find the equation of an ellipse with center at 0, 0, one vertex at 0, negative 7, one end of minor axis at 5, 0. From the given information, we have center at the origin, a vertex at 0, negative 7, and one end of the minor axis. Hence, we have a co-vertex at 5, 0. Hence, we can get the value of A as equal to 7 and B as equal to 5. Since A is greater than B, we have an ellipse with major axis along the y-axis. So we have the equation x squared over b squared plus y squared over a squared equals 1. A squared is equal to 49 and b squared is equal to 25. Hence, the required equation is x squared over 25 plus y squared over 49 equals 1. Example number 3, sketch the ellipse 9x squared plus 25y squared is equal to 225. Let us first translate the equation to its standard form. So we have 9x squared plus 25y squared is equal to 225. We divide both sides of the equation by 225. We will have x squared over 25 plus y squared over 9 is equal to 1. Since a squared is greater than b squared, we have a squared is equal to 25 and b squared is equal to 9. Hence, a is equal to 5 and b is equal to 3. To find the coordinates of the focus, we will use the relation c squared is equal to a squared minus b squared. Then c squared is equal to 25 minus 9, that is equal to 16. Hence, we have c is equal to 4. So we have an ellipse with major axis along the x-axis, and we have the coordinates of the vertices. Since a is equal to 5, we have the coordinates of the vertices v at 5, 0 and v prime at negative 5, 0. Also, b is equal to 3, so we have the coordinates of the co-vertices b at 0, 3 and b prime at 0, negative 3. Since c is equal to 4, the coordinates of the focus or the foci will be f prime, negative 4, 0 and f at 4, 0. Let us graph the ellipse. So we have the y-axis and the x-axis. We have the foci at negative 4, 0 and 4, 0. We have the vertices at 5, 0 and negative 5, 0. Also the co-vertices at 0, 3 and 0, negative 3. Hence, we have the graph of the ellipse. The focus directrix property of an ellipse. We defined a parabola in terms of a focus and directrix, but we made no mention of the directrix in defining an ellipse. It turns out, however, that an ellipse has directrix. In deriving the equation of an ellipse, we arrived at the equation negative a times the square root of x minus c squared plus y squared equals cx minus a squared. This equation implies the existence of a directrix, which is evident after a slight modification or algebraic manipulation. If we divide both sides of the equation by negative a, we will have the square root of x minus c squared plus y squared is equal to a minus cx over a, which can be rewritten as square root of x minus c squared plus y squared equals c over a times the quantity a squared over c minus x. The left member of this equation is the distance from the point xy of the ellipse to the focus C0. The factor a squared over c minus x of the right member is the distance from the point of the ellipse to the line x is equal to a squared over c. And the factor c over a is a constant between 0 and unity. Here we have a proof based on our definition of an ellipse using the focus and directrix. Through the theorem, an ellipse is the set of points in a plane such that the distance of each point of the set from a fixed point of the plane is equal to a constant between 0 and 1 times its distance from a fixed line of the plane. So sometimes an ellipse is defined in terms of focus and directrix. When so defined, it is possible to prove the statement contained in our definition of ellipse. The line x is equal to a squared over c is the directrix corresponding to the focus C0. It would be easy to show that the point negative Z0 or the f prime and the line x is equal to negative of a squared over c constitute another focus and directrix. This fact, however, is geometrically evident from the consideration of symmetry. Let us have example number 4. Identify the properties of the ellipse x squared over 36 plus y squared over 20 equals 1. Since a is greater than b, then we have a squared is equal to 36, square root of both sides, a is equal to 6. Then we have b squared is equal to 20. Then b is equal to 2 square root of 5. From the relation c squared is equal to a squared minus b squared, we have c squared is equal to 36 minus 20. C squared is equal to 16. Then c is equal to 4 by getting the square root of both sides. Hence, we can have the properties of the ellipse. We have the vertices at points a is equal to 6. Hence, we have 6, 0, and b prime at negative 6, 0. The major axis is 2a, so we have 12 units. Since b is equal to 2 square root of 5, then we have the co-vertices at points b, 0, 2 square root of 5, and b prime, 0, negative 2 square root of 5. Minor axis is 2b, so we have 4 square root of 5. The center is at the origin, so we have 0, 0. C is equal to 4, and the major axis is along the x-axis, Hence, the coordinates of the foci, f prime, negative 4, 0, and f at 4, 0. The ends of latus rectum at negative 4, b squared over a is 20 over 6, that is 10 over 3. Also, we have negative 4, negative 10 over 3. Also, we have the ends of latus rectum at positive 4, 10 over 3, and positive 4, negative 10 over 3. The length of latus rectum is equal to 2b squared over a, so we have 20 over 3. The directrix will be the line x is equal to positive a squared over c, so that will be 36 over 4, or x is equal to 9. And also we have x is equal to negative a squared over c, so that will be x is equal to negative 9. Let us have example number 5. Identify the properties of the ellipse y squared over 169 plus x squared over 144 equals 1. Since a is greater than b, so we have a squared is equal to 169 and a is equal to 13. We have b squared equal to 144, then b is equal to 12. From the relation c squared is equal to a squared minus b squared, c squared is equal to 169 minus 144, then c squared is equal to 25, and getting the square root of both sides, we have c is equal to 5. Then we have an ellipse whose major axis is along the y-axis. Hence, the vertices of the ellipse will be at b, 0, 13, and b prime at 0, negative 13. The length of the major axis is equal to 2 times 13, that is 26. The co-vertices will be at point B, 12, 0, and B prime, negative 12, 0. The length of the minor axis is 2b, then we have 2 times 12, that is 24. The center is at the origin, and since c is equal to 5, the foci will be at points f, 0, 5, and f prime, 0, negative 5. The ends of latus rectum will be at negative b squared over ac, negative b squared over a, negative c, so that will be negative 144 over 13, 5, negative 144 over 13, negative 5. Also, we have 144 over 13, 5, and 144 over 13, negative 5. From the ends of the latus rectum, we can get the length of the latus rectum as equal to 288 over 13. The directrix will be the line y is equal to a squared over c, that is 169 over 5, and y is equal to negative 169 over 5. Exercises on this topic may be downloaded from the link given on the description of this video. That will be all. Thank you for watching. Please subscribe for more math lessons.